In today's lesson, we are going to expand a little bit on what we talked about in the last lesson about this idea of rationalizing the denominator. So if you remember, that's the idea that the denominator needs to be a rational number. In other words, I can't have any radicals or square roots in this case floating around in my denominator if I have a fraction. So what we're going to talk about today is, if you look down at your examples, you kind of see some examples. What happens if I have a fraction with a radical in it, but I'm adding or subtracting that radical? So because now I've got addition and subtraction going on, I can't just multiply by whatever the square root is to get rid of it. That doesn't work with adding and subtracting. It only works if I'm just multiplying. So if we have adding or subtracting, we need to deal with it a slightly different way. We're going to talk about how do we do that today. So how we do that actually is going to involve using something that we talked about from our quadratics, and that is the difference of squares rule. So we need to review what that rule is if we're going to use that rule. So the difference of squares lets us take two binomials that have the same terms, but one we're adding and one we're subtracting, so it would look like this. And if you remember, if we multiply this out, what ends up happening is we have a first term, a times a is a squared. But then the middle terms cancel each other out because I end up with a positive ab and a negative ab. So those are going to cancel out and they won't be there. So that takes care of my inner and my outer. They wipe each other out. And then I'll have my last term, b times negative b minus b squared. So I end up with the statement a squared minus b squared with those middle terms missing because the middle terms end up canceling each other out. So what we're working with, so these two starting terms, so when you have two binomials that have the same terms but opposite operations, so basically something like this, they look the same but one's adding or subtracting, those binomials get a special name. They're called conjugates. So it's kind of a fancy version of opposites, conjugates. So we can use conjugates and the difference of squares to get rid of a radical in the denominator, because remember we can't have radicals in the denominator when we have addition or subtraction going on. So it would work something like this. So if we take our first example, 4 minus the square root of 2, so the conjugate or the other part that goes with that, if I wanted to multiply that, would be 4 plus the square root of 2, and that's going to create a difference of squares problem where the middle terms cancel out, which is going to make it so that we end up not having any square roots after we multiply that out. But we also talked about the fact yesterday that if I multiply the denominator, I have to multiply the numerator by the exact same thing so that I'm basically multiplying by 1 because anything over itself is 1. So whenever I multiply the bottom, I have to multiply the top so that I'm not actually changing the value of the fraction. The numbers look different, but really I'm just multiplying by 1. So now I can go through and I can clean this up. So on the bottom, we're going to be able to use our difference of squares rules. So on the bottom, I'm going to write out kind of literally what the difference of squares does, and then we'll clean it up. So difference of squares says that I could just take these two terms, square them, and subtract them, and not worry about the middle term. So if I use the difference of squares shortcut on the bottom, I would end up with 4 squared minus the second term is the square root of 2 squared. So that's literally just using the difference of squares shortcut, and then we can clean that up in a minute. Now on the top, I have 3 times 4 plus the square root of 2. That I'm going to have to use some distributive property for, because I have one number times a sum. So I have to distribute the 3. So 3 times 4 is 12, and 3 times the square root of 2, I can't actually multiply those, so I would just leave it literally as 3 times the square root of 2. So it would look like that. So now we can go through and we can just do a little bit of cleanup. So especially on the bottom here, we can clean up the bottom. So we're going to leave our top alone for just a second here. So on the bottom, we get 4 squared is 16. square root of 2 squared is really the square root of 2 times square root of 2. Well, that's the square root of 4, which is 2. So basically the square and the square root wipe each other out. Square root of 2 squared is just 2. Squares and square roots undo each other. And then we could clean that up even more and say, okay, 12 plus 3 times the square root of 2 over 14. So now we are honoring all three of our simplifying with radical rules. We do not have any perfect square factors left in the radicand because the radicand's 2. That's not a perfect square. We do not have a fraction in the radicand. 2 is a whole number. And there are no radicals in the denominator of our fraction because the denominator of our fraction is now 14. So that means we are honoring all three of our rules. So that would be considered a simplified answer. And that's as far as we can go with that. So let's look at another one. So you can see the second example problem is a little busier. It's got a little bit more going on, but I want to show you that you can take a problem that looks a little busier and it's still the exact same basic idea. So if we want to get, we actually have 2 square roots in 2 different places in the denominator, but that difference of squares multiplying trick is going to wipe out all of the square roots in the denominator. So the conjugate or this, or the opposite part of this that will make our difference of squares pattern work would be to multiply it by 2 times the square root of 7 minus 3 times the square root of 3. But if I multiply the bottom by that, I also have to multiply the top by the same thing so that overall I'm really just multiplying by 1 and not changing the value. So we're going to have the same thing going on as the last problem. I need to use distributive property on the top and difference of squares on the bottom. So I am literally just going to write out what this looks like and then we'll get it all cleaned up in just a minute. So on the top we have to do some distributive property. So I'm literally just going to write out the multiplication and then, like I said, we'll clean it up. So it's going to be 2 times the square root of 5 times 2 times the square root of 7 and then minus 2 times the square root of 5 times 3 times the square root of 3. So that's literally just, that's what happens when we distribute that. Now on the bottom, we've got our difference of squares going on. So the middle terms are going to cancel out. So we end up with just the first term squared minus the last term squared. So the first term is 2 times the square root of 7. So I want to take that whole thing and square it minus the second term. So take that whole thing and square it. So now we just have a whole bunch of cleaning up to do. So we've got this all worked out. We just need to clean it up. So on the top, remember, we have a rule that says that square root of 5 times square root of 7, we could put those, that's our product property with radicals, we can put those together under the same square root sign. And instead of saying square root of 5 times square root of 7, we could just say square root of 35. And we can also multiply the 2's together on the outside. So that would turn this into 4 times the square root of 35, which is much nicer to look at. And then we can do the same thing in the other part. So we can multiply the 2 times 3 together, that's 6. And then we can put our 2 radicals together into a single radical. Instead of saying square root of 5 times square root of 3, we could say square root of 15. So that takes care of the top. Now, the bottom. So but you have to remember with this, and I'm going to kind of do a little aside here because it helps if you see this expanded out. When you square a number, you're actually multiplying it by itself. So 2 times the square root of 7 squared is really 2 times the square root of 7 times 2 times the square root of 7. So we can do the exact same thing we were doing up top, and we could say, okay, I'm going to go ahead and multiply the 2's together, and that's going to give me 4. And I'm going to do square root of 7 times square root of 7. Well, square root of 7 times 7 is the square root of 49. So square root of 7 times square root of 7 really just works out to be 7. So what I end up with there is 4 times 7, which is going to end up being 28. We'll get to that in a minute. We're just trying to show our work. And then I could do the same thing in the other part. So square root of 3 squared is really 3 square root of 3 squared is really 3 times the square root of 3 times 3 times the square root of 3. So I can do the 3 times 3, and I can do the square root of 3 times the square root of 3 to kind of get those gathered together. So 3 times 3 is 9. Square root of 3 times square root of 3 is 3, if you walk through the steps for that. So I end up with 9 times 3. So notice I do not have any square roots in the denominator anymore, which means that this difference of squares trick did its job. But I do still have a little bit more cleaning up to do because I can do 4 times 7 and my 9 times 3. So if I pull that out, then I can go ahead and clean all that up. So 4 times 7 is 28. 9 times 3 is 27. So this is really 28. This is really 27. Well, 28 minus 27 is 1. So I can even take that a step further because we know that anything over 1 is really kind of like a whole number. It's like dividing by 1 as itself. So rather than saying 4 times the square root of 35 minus 6 times the square root of 15 over 1, I could just say, okay, the answer is 4 times the square root of 35 minus 6 times the square root of 15. And that would be my final answer. And if I check that, I am following all of my rules because square root of 35 and 15, neither of those have perfect square factors. So that's rule number 1. 35 and 15, neither of those are fractions. So that's rule number 2. I don't have any fractions in my Radican. And I completely eliminated my denominator in this problem because I turned my denominator into 1, so there's no denominator left for me to worry about having radicals or square roots in. So I am now following all 3 rules, which means that is considered a simplified answer. So that is how you deal with square roots in the denominator when you have addition or subtraction. So the practice problems you guys are going to try today are going to be kind of like the practice problems that we were just working with here for you to practice this idea of using our difference of squares rule to get square roots out of the denominator. So when you're ready, you can go